Hey, everybody. So as you can see, we are talking about limits at infinity, which is a phrase that's really not quite correct in what it implies, right? We don't get to infinity. There's no at infinity. It's just a symbol we use when we're talking about getting large without bound, or getting very negative without bound, things like that. So I'm going to start with definitions of what I mean by this, or at least one type of limit. We'll see there's a couple different kinds of limits at infinity. And then we'll do some examples and see a few things that come out of that. So let's just start with our definition. We will write the following set of symbols: the limit as x goes to infinity of the function f of x equals L. We write this to mean, right? So this means we can make f of x arbitrarily close to L by taking x to be sufficiently large. Right, so similar to limits from earlier in the videos where we were approaching, x was approaching a number instead of x just going off towards infinity, but we still have this number that the function's getting closer and closer to, right? So when we would say the limit, we would say something like the limit as x approaches a of f of x equals L, we would say we can make f as close as arbitrarily close to L by making sure that x was sufficiently close to a. Well, now instead we're saying, well, look, this function gets closer and closer to some number L. If you tell me how close you want it, I'm just going to tell you how big I have to make x to get it that close, right? That's the sufficiently large part, okay? We can do a similar thing to negative infinity. We take x, the limit as x goes to negative infinity of f of x equals L, means a similar thing. We can make f of x arbitrarily close to L by taking x to be sufficiently, I'm just going to write this, large negative. Right? So what do I mean by that? I just mean it's a very large number, except it's negative. So you can say something like the absolute value of x is getting very large, but the sign of x is negative, okay? So we're just getting really, we can talk about these both as getting far away from zero, right? One is far away to the right on the number line, one is far away to the left. So there's our first kinds of limits at infinity. Let's do an example of one that hopefully will help us explain these definitions. Let's do it over here. We have some space. So I might claim, for instance, that, or I do claim that the limit as x goes to infinity of 1 over x is equal to 0. Okay. So what I mean is if I make x larger and larger and larger and larger, the values of 1 over x get closer and closer and closer to 0. And I can make them as close as I want by taking x to be large enough. So we can see this on a graph. Let's start there. Here's the graph of 1 over x, right? And so we are looking on the right-hand side of this graph, far away from 0, right? So we can see as we get past 2, 4, 6, 8, 10, it's getting closer and closer to 0. Right, and as it gets out here, if we were to go very far away, zoom way out, and then zoom back in, here we are at 12,000. Right, we're incredibly close to 0, right? This line, the black line is the x-axis, that's 0. And then the red line is below 0.000001, right? So this is incredibly small, incredibly close to 0. And if I keep going out to larger and larger x values, this is all going to get even closer, okay? Let's go back to a more normal zoom. Okay, so that's the idea. can we really prove that this is true? Let's do what I'll call a soft proof of this, right? So can we make, right? Let's think about this like a challenge. We're going to be close to 0, right? So first of all, notice we're putting in positive numbers. So positive numbers are coming out when we take the reciprocal. So close to 0 means we're between 0 and some positive number, right? If I have a number line, here's 0, right? Close, just how these are going to, maybe this is 1/2 and then this is 1/4. We can keep making some demands on how close it could be. So for instance, I could say, can I make f of x less than, 1 over x, just I didn't name it f. Can I make 1 over x less than 1/10 from 0, right? In other words, I need 1 over x to be between 0 and 1/10. Well, it's easy to see that if I demand that x be greater than 10, then 1 over x is less than 1/10. And we already know it's positive, so we kind of get that 0 for free. Okay? And so somebody could say, okay, but how about keeping it less than 1/10,000th from 0? So we want this. And then I can just say if x is greater than 10,000, 1 over x is less than 1 over 10,000. And again, it's positive, so it's going to be above 0. So it's easy to see here, right? Any demand that's made of b, I simply take, instead of 1 over 1,000, 1 over 10,000, I will make x be bigger than the reciprocal, and we end up with 1 over x being smaller than the reciprocal, okay? Or smaller than the original. So we can make this more general, right? I want to know that for any number, any large number you give me, I can always do this. Well, that's easy enough to say, can I make 1 over x less than, and I'll just use an abstract small number, I'll call epsilon. This is a common symbol to use for a small number, epsilon. Can I make 1 over x less than epsilon from 0? Right? This means that 1 over x is between 0 and epsilon. Well, if I take x to be greater than 1 over epsilon, then 1 over x is less than epsilon. And since these are all positive, we know we're bigger than 0. Okay, so it's just kind of a formal way to write down algebraically that I can always do this. There's no positive number that I can't take 1 divided by it and look at the numbers bigger than that. So I'll always be able to do this, okay? So we now have this limit, and we can take this, this now is a limit that we can use without having to prove each time. And in fact, we get even better. We can do the exact same thing, or almost the exact same thing, as we go to negative infinity. It also approaches 0. And so these two limits, we can now consider part of our toolbox and use them to find other limits. Let's do that right now. Let's say I have the limit as x goes to infinity of 1 over x to the n. So we've got this, let's say, positive exponent on x. Well, let's call it an integer for now. It's a positive integer. And we can still use our limit laws, right? I'm not going to prove that that still works for these infinite limits, but they almost all work. The one thing that doesn't work is plugging in infinity, right? We had one of our limit laws early on that said if something's continuous, we can simply plug in the value a when we're taking the limit as x approaches a. Infinity is not a number. You can't evaluate with infinity, right? So I can't put infinity in for x and see what I get here. But I can use the other limit laws. And the limit laws I want to use here has to do with the limit of products. If n is a positive integer, then 1 over x to the n is 1 over x times 1 over x times 1 over x right? N factors of x, or of 1 over x. Well, we have a limit law that says I can take the limit of each factor separately and then just multiply them all together, right? In other words, the limit of a product is a product of limits. So I take each limit of 1 over x, and we get, there'll be n of these factors. And we just saw that the limit as x goes to infinity of 1 over x is 0, so we're multiplying 0 by itself a bunch of times, and we get 0. So it turns out 1 over any power of x, positive power of x, we'll typically use integers, maybe rational ones, but we can't quite show it with this, but in general, this works for any positive integer, right? That bottom is growing huge, right? If that's x cubed and we're putting in larger and larger numbers, we get 1 over a billion cubed. It's incredibly small. 1 over a trillion cubed is incredibly small. We can just keep making it smaller and smaller by getting larger and larger values of x. All right, let's try another example. Let's take the limit as x goes to infinity of this rational function. Okay, so what we might try is one of our limit laws. The limit as x goes to infinity of 3x squared minus 1. The limit as x goes to infinity of x squared minus 1. That's a reasonable thing to attempt. And we have a polynomial in the numerator and the denominator. We're letting x get very large. In fact, we have quadratic polynomials with positive leading terms. What's going to happen to 3x squared minus 1? Oh, doesn't really matter much, but this was supposed to be a 3. What's going to happen to 3x squared minus 1 as x gets larger? Taking large numbers, squaring them, they get larger. Multiplying by 3, they get really large. We subtract 1, but we've done all this other stuff to make it bigger, right? 1,000 squared times 3 minus 1 doesn't really matter much there. 1 billion squared times 3 and then minus 1 doesn't really matter much there, right? So both of these get large. There's no end to how large they get. The bigger x gets, the bigger these two things are. And so what we would say is that their limits, the limit in the numerator is equal to infinity, okay? As is the limit in the denominator. Okay, now, a couple things about this. What do I mean when I write this? What I mean is I can make either of these expressions, 3x squared minus 1 or x squared minus 3, right? Whenever I write the limit of something goes to infinity, the limit as x goes to infinity of 3x squared minus 1 equals infinity, it's similar to what we meant when we had vertical asymptotes and we were doing limits, that we can make this function as large as we want. Instead of getting close to some number, we just make x larger and larger. So in fact, we're saying these limits don't exist, but we're still conveying some information with the symbol to get as large as we want. And sometimes you'll have functions that do this, but they go in the negative direction and you have the limit equal to negative infinity. Okay, now here's what we are tempted to do. The limit in the numerator is infinite. The limit in the bottom is infinite. In fact, in other words, they don't exist. And we might want to do something like this. Anything over itself is 1, and claim that this limit is 1. This is absolutely nonsense and not true. Okay, so this thing I just did is not true, right? We can't divide infinities, right? Infinity is not a number. Division is a thing we do to numbers. We don't know how division works for infinities. But we can't assume it follows the same rules, that when we have the same symbols over each other, then they cancel out or we get a 1, right? It's the same as 0. 0 over 0 we can't take to be 1, right? So this is, now I've got double negatives. Let's get rid of, right? It's even silly to say infinity over infinity does not equal 1, this is just a symbol we should never write, right? We don't need this. This doesn't happen, right? Similar how this is not equal to 1, right? These are what we call indeterminate forms, okay? Now, it doesn't mean we're lost. It doesn't mean this limit doesn't exist. Both things are growing large, but when you have a fraction where the numerator is getting really big and the denominator is getting really big, what happens to their quotient? It depends. Different things can happen. Let's try to figure out what happens in this case, okay? We're going to use a trick. We've used a similar trick to this in when we first looked at limits, which was, remember when we were looking at limits as x approached some number that caused us to have a 0 in the denominator. And so what we would do is manipulate the expression algebraically until we got one that didn't have that problem. We're going to do a similar thing here and manipulate this this expression, our function 3x squared minus 1 over x squared minus 3. We're going to manipulate it algebraically until it doesn't end up with this infinity over infinity problem. And here's a common trick when you have rational functions. You look at the denominator, look at the highest power of x in the denominator, and multiply the whole fraction by the whole rational function by 1. But the way in which we multiply it by 1 is by taking, again, that highest power in the denominator, in this case, x squared, and we multiply by 1 over that, over 1 over that. We're multiplying by 1, okay? Remember, we're looking as x gets really large. I don't have to worry about x being equal to 0, so the fact that I'm doing 1 over x squared is not of consequence. We don't have to stress over that. So let's see why we did this. The limit as x goes to infinity. When I distribute this in the numerator, 1 over x squared times 3x squared gives me 3. And then I get 1 over x squared. In the denominator, I'm going to distribute, and I get 1 over x squared times x squared. That gives me 1, and I get 3 over x squared. Now I'm going to use the limit law that lets me take the limit in the numerator and the denominator separately. Now I'm going to use the limit law that lets me split up over these sums. Whoops, this is x goes to infinity, 3 over x squared. So let's think through a few of these limits. Let me start a new line. I should have worked down. This is a little bit ugly. So where we've gotten to is that this limit is equal to, oops. All right, we're going to start to simplify this expression. So this first part, the limit as x goes to infinity of 3, is asking the question, what happens to the number 3 if I make x bigger, right? And that has an easy answer, nothing. 3 doesn't change, it doesn't care about the value of x. 3 is 3. Then we're subtracting the limit as x goes to infinity 1 over x squared. We just showed a moment ago that for any positive exponent on the denominator, right? What we showed up here, we end up with a limit of 0. So that piece there is 0. In the denominator, the limit as x goes to infinity of 1 is just 1, just like 3 was just 3. 1 doesn't care what x is doing, it's still the number 1. And I'm going to use one more limit law here. Remember, we have this limit law that lets us slide constants through. So I can take that 3 out front. I get the limit as x goes to infinity of 1 over x squared, which we just saw up above is 0. So now I've got 3 minus 0 or 3 over 1 minus 3 times 0, which is 0. So I've got 3 over 1 or 3. And that's the limit of this function, okay? This is a super common trick when we have rational functions, looking at what the highest power in the denominator and multiplying by the reciprocal of that over itself. So you're multiplying by 1, you're not changing the value. Let's end by looking at a picture of this function. So here is the function. Let's put in y equals 3. Let's make it a different color and a little thinner maybe. How about, and let's make it dotted. So there's our function that's approaching, right? This line is y equals 3. And that blue graph, our function, notice as we go far away from 0, right? It gets really hard to see here, but that blue line looks like it's sitting right on top of that. In fact, it's just a little bit above it all the time, right? There's a little bit of space between them, but it gets closer and closer to it as we go out to infinity. We didn't do to negative infinity. It turns out it does the same thing over there. We'll talk about those in a later video, but I just wanted us to see this, right? That this is the case where we have a horizontal asymptote. In fact, whenever we have a limit like this, when we have a limit as x goes to positive or negative infinity, that is a horizontal asymptote. That's our definition of horizontal asymptotes, that the limit of a function, if we have the limit of a function equals some finite number, then that is the horizontal or a horizontal asymptote for the function. Let's look at how close it's getting to 3, right? Here's that function evaluated at 2. It spits out 11, right? So it's not close to 3 at all. It doesn't near 0. Things are a little bit messier, but even just getting as far away as 6, we already get ourselves down to a value of 3.24. And you notice as I go through 100, 1,000, and 10,000, by the time we get out to 10,000, we've got 3.000001. I think I said the right number, right? We're just barely above 3, and 10,000 is really not that big in the grand scheme of things, okay? One way to see what's going on, right here I have evaluated the numerator and the denominator. When we look at 10,000 as our inputs, 3 times 10,000 squared minus 1 is 299,999,999. That's basically 300 million, which is what this would be without the minus 1, right? When we're looking at 3x squared minus 1, for x values that are really, really large, these are basically the same number, right? If someone told you that they were going to pay you $300 million to do something, when you finish that thing, you were $1 short, it wouldn't be worth opening your mouth to tell them, right? You have all these other dollars. That $1 feels very insignificant at that point. Similar thing happens to x squared minus 3. When x gets very, very, very large, the minus 3 doesn't really matter. Here we have our 10,000 squared, right? So we're instead of getting 100 million, we're getting 99,999,997, right? Again, if you were asked somebody to watch $100 million for you and you came back and there were $3 missing, it's unlikely you would notice or care. Right, so for these very large numbers, these things become fairly equivalent. What that means is 3x squared minus 1 over x squared minus 3 is close to 3x squared over x squared, which of course is just 3. Again, I don't have to worry about canceling zeros because we're dealing with large numbers, so zero's not in the game right now, right? And to be clear, it's never equal to 3. I'm not saying these are equal or at some point out there they become equal, but this approximation is giving us some intuition about why that limit turned out to be 3. Okay, that will do it for this one. I'll point out one last thing. Notice that 3, the limit that we got of 3 is equivalent to the ratio of the coefficient of these 2x squared terms. That's not an accident. You can think about why that might be and what that might mean for other rational functions and different kinds of functions, but we'll do more of that in the next video. That is really it for this one. Thanks, everybody. I will see you next time.